This is the Algebra 2 practice test for sections 4.1, 4.2, 4.4, and 4.5, and it starts with our quadratics. So quadratic functions and transformations, we want to graph each quadratic function, name the vertex, axis of symmetry, the maximum or minimum value, and the domain and the range of each function, just like we did in the homework as we went through this chapter. So what we need to remember is y equals a times the quantity x minus h squared plus k, and that h and k are the vertex. So keep in mind that the x value is always the opposite of what we see. So when I look up here and see x minus 2, I realize my vertex is actually a positive 2. But k is normal, so this k in the back of 3, 2, 3 will be the vertex. And the axis of symmetry is always x equals h. So that will be x equals 2 because our vertex had an x coordinate of 2. Now, the key for this next part, max or min, is knowing which way this is going to open. And that comes from looking at the a value that's out in front. And this one doesn't have an a, so that means it was a positive 1. And that tells me this parabola is going to open up. So what we have here is a minimum, and the minimum is the vertex, 2, 3. So now the domain of this, the domain is going to come from any x values that we can use in this formula. And the only way that that is ever restricted is if we have a square root in our equation, or if we have to use division, and there is neither one in this problem. So our domain is all real numbers. But our range is going to come from our sketch. So we look over here and we realize that 2, 3 is the lowest value that we're going to have, and 3 is the y value. So if I need 3 and above, I'm going to have to say y is greater than or equal to 3. And that again we can get from our graph as well. So let me go ahead and move this up a little bit if it will let me. There we go. And we will graph this. So we have a vertex at 2, 3, like so. We know it's supposed to open up. We'd like to have some other points. So what we'll do is we'll pick some numbers that are close to 2 that would be nice to work with, like 0 and 1. So what we do with those numbers is put them all the way back up into this equation. And that would mean we need 0 minus 2, the quantity squared, so that's negative 2 squared, which is 4, and 4 plus 3 is 7. So all I'm doing is putting that 0 into the equation and then doing the math. And then with a 1, y equals 1 minus 2 squared plus 3. 1 minus 2 is negative 1, negative 1 squared is 1, and 1 plus 3 is 4. So I have 1, 1, 2, 3, 4, and I have 0, 7, 1, 2, 3, 4, 5, 6, 7. And then I know where that axis of symmetry is. It's right through the vertex. So I'll go ahead and graph that helper line, x equals 2 on here, and then use symmetry to go equal but opposite on the other side of my symmetry line. And then go ahead and graph. Now if you didn't think that was enough, you might put either a negative 1 in, or 1, 2, 3, 4, probably a 5. So let's see what happens if we put a 5 back into this. 5 minus 2 would be 3. 3 squared is 9. 9 plus 3 is 12. So we're already off of our negative 10 to 10 grid. So these would be enough points for us to get a really nice parabola out of that. So we did everything they wanted. We graphed it. We gave them the vertex, axis of symmetry. We gave them the minimum value and the domain and range of that graph. So that was vertex form. Now they don't all come in vertex form. Y equals a times the quantity x minus h squared plus k. So, oh, I must have put that down here below. There it is. And the screen is doing a little bit of the hoppity stuff here. Here we go. So graph each quadratic function, name the vertex, axis of symmetry, maximum or minimum values, and the domain and the range of each function. So what we have to do is figure out, well, what form is this in? And once we know that form, work from there. And this is probably needing to be slid over a little bit so we can see all those pieces. All right, this is a little goofy, so I will have to write the information about axis of symmetry, vertex, max, min, domain, and range to the left of those words. So we're graphing this quadratic, and I realize this is in standard form. And to find the vertex, when you have a quadratic in standard form, we use negative b over 2a. So this will be negative of negative 12 over 2 times negative 2. Well, that's going to be 12 over negative 4, which is negative 3. So that is our x-coordinate for our vertex. To get the y-coordinate, we have to take the negative 3 and put that back into the function. So we're going to need negative 2 times negative 3 squared minus 12 times negative 3 plus 11. Well, negative 3 squared is 9. Negative 2 times 9 is negative 18. And in the middle we have plus 36, so negative 18 plus 36 is 18. 18 plus 11 is going to give us 29. So negative 329, if that truly is going to be my vertex, I can't go by ones. I have to be able to fit that 29 on there. So my y's for this one are going to have to go by at least 3. On the x's, I should be okay going by ones, but not on my y's. So negative 329, 1, 2, 3, and then not quite up to the top there. And I notice this has a negative in front of it, which tells me this is going to open down. So now my vertex is at negative 329. My axis of symmetry is going to be x equals negative 3 because it's always going to be a vertical line through the x-coordinate for the vertex. And because I know this is going to go down, I know that this is actually a max at negative 329. It is a maximum. And my domain for this, again, I don't see any division, I don't see any square roots, so it's going to be all reals. But my range, this y value of 29 up here, that's the highest y value we're going to use. So y is going to be less than or equal to 29. And now we would need some more points. So what we would want to do is make a table and put some numbers in and see what we get. All right, so a negative 2 would be negative 2 squared is 4. Negative 2 times 4 is negative 8. Negative 12 times negative 2 is 24. So we'd have 24 basically minus 8, which would give us 16, and 16 plus 11 would be 27. And you could actually do all of that on your graphing calculator if you use parentheses like I have them right here. Negative 2 times negative 1 squared minus 12 times negative 1 plus 11. Negative 1 squared is 1, so we have negative 2 plus 12 is 13. 13 plus 11 is 24. And then we could put a 0 in there. So negative 2 times 0 squared minus 12 times 0 plus 11, and that would give us 11. So at negative 2, we have 27, and at negative 1, we have 24, 3, 6, 9, 12, 15, 18, 21, 24. And at 0, we have 11, 3, 6, 9, and about there. And then we could go ahead and use the axis of symmetry to go equal but opposite on the other side. And draw our parabola with arrows, of course, showing that we know that that's going to go forever. So there it is. And again, really we can do almost all of this without having to graph it, just by getting a little picture in our mind of what's going on. Number 3 says we're not going to graph this time. Without graphing, name the vertex, axis of symmetry, the maximum or minimum value, and domain and range, and the transformation of the function when compared to the parent, which was just x squared. So I notice that this is in vertex form. And I realize I need the opposite of whatever the x is for my vertex, so that'll be a positive 3 and a 2. My axis of symmetry is always x equals whatever that x equals, because that's our h value. And I see there's a negative 4 in front, which tells me this is going to open down, so this is actually going to be my max right here at that vertex of 3, 2. Domain, all reals, just like the other ones were. But our range, well, the highest value we get to for y is 2. So y is going to be less than or equal to 2. Transformations, that's where we work from left to right. And we say, all right, let's go back up here and see the first thing we see is a negative 4. So the negative is a reflection over the x-axis. The 4 is a vertical stretch, factor of 4. Then we have the x minus 3. Well, that is translate 3 units to the right, keeping in mind that that's the opposite of what we see, and a plus 2 would be 2 units up. So all the numbers have been explained. Reflection over the x-axis took care of the negative. Vertical stretch factor of 4 took care of the 4. Translate 3 units to the right. There's our opposite of our x minus 3. And then 2 units up because k is perfectly normal. And that took care of all of the transformations that we needed to talk about for problem number 3. Problem number 4 says the students in Mr. Wilson's physics class are throwing golf balls. The flight of group A's ball is modeled by the equation y equals negative 0.14x squared plus 0.68x plus 6, where the height y in feet can be written as a function of x, time, and seconds. And we want to know, when did the golf ball reach its maximum height? Well, as I look at this equation, I realize this is a downward opening parabola, like so. And if I'm going to answer any questions about the maximum, I need that point right there, which just happens to be the vertex. So I need to figure out what my x value is for the vertex, and that's our negative b over 2a when we're in standard form. So negative 0.68 divided by 2 times negative 0.14. And that comes out to be about 2.43 seconds. So that's how long it's going to take it to get its maximum height. And then it says, what is that maximum height that the golf ball reaches? Well, to get that, we have to put 2.43 back in there. So y equals negative 0.14 times 2.43 squared plus 0.68x. Sorry, don't want the x there anymore. 0.68 times 2.43 plus 6. And for that, we just go ahead and grab a calculator, and that will be 6.83 feet. Okay, sorry, I was going to cough there. I didn't want to cough into the microphone. So 6.83 feet. Notice those are just the coordinates of the vertex. That's all that is. So C says we've got Bobby, and he throws the golf ball to Connor, who makes a spectacular catch of that ball 6 feet above the ground. Oh, well, this is where the stuff goes for above the ground, so that means we're going to have to put a 6 in there. And it says, how long was the golf ball in the air? Oh, well, let's see. So, first things first, that means I want to know what the x value is for that coordinate. And that coordinate is a 0. And how we find zeros is by factoring, which means I need to have a 0. So I'm going to have to subtract 6 from both sides. And then I really, really hope that I can factor something out and make this an easier problem, and I realize I can take an x out of both of those. In fact, I could take a negative x out of that. And then I need to find the zeros. Well, the zero for this one is going to be x equals 0 because 0 times anything is 0. Pretty obviously, that's this point right here. I don't want that one. I want the other one. So the other one comes from 0.14x minus 0.68 equaling 0. So we would add 0.68 to both sides. 0.14x will equal 0.68. And then we will divide both sides by 0.14. And x will equal 4.86. And our x values were in seconds. So whenever we're solving, remember the only way we've done that so far in this chapter is by factoring. So we have to factor to solve. Next up, to make an enclosure for chickens, a rectangular area will be fenced. There is 120 feet of fencing material, so all the way around. That's our perimeter. What quadratic function represents the area of the rectangular enclosure? Well, I don't know the dimensions. I'm just going to put an X there. And here's what I know. I don't know these either. But I do know that 120 is going to equal 2x plus 2y. And I can't use both variables at once. So what I need to do is solve this for y, so I have something about x that I can put in there for y. So I'm going to subtract 2x from both sides and get 120 minus 2x equals 2y. Divide everything by 2 and get 60 minus x equals y. So that allows me to take those y's off of there and make this 60 minus x. That way I don't have two variables. So it says what represents the area of that rectangular enclosure? Length times width, x times 60 minus x. But we would certainly go ahead and multiply that out. And I would like to have that in standard form. So negative x squared plus 60x. B says, what dimensions will maximize the area of the enclosure? Well, that's going to be the vertex because this is opening downward. And this is in standard form, so we'll do x equals negative b over 2a, which would be negative 60 over 2 times negative 1. Negative 60 divided by negative 2 is 30. So we'll have 30 feet for one dimension. Well, the other dimension is 60 minus x. So that's going to be 60 minus 30, which is also 30. So to maximize the area of the enclosure, we need 30 feet by 30 feet. And just like all of the problems that we had in the homework about these, it ends up being a square, 30 feet by 30 feet. And there are the dimensions that would maximize that chicken enclosure. Now we get to the things that'll go a little faster in most cases, and that would be the problems where we're just factoring. So I look at number 6 and I think, is there a greatest common monomial factor? The answer is no. Is this a perfect square trinomial? No, negative 12 is not a perfect square, but maybe I can use some good old-fashioned factoring and find two numbers that multiply to negative 12 and add to 4. And sure enough, plus 6 and minus 2. I go over to number 7, and I'm looking for a greatest common monomial factor for 9, 12, and 4, but there aren't any. And then I think, well, hang on a second. 9x squared, that's a perfect square of 3x, and 4 is a perfect square of 2. If I multiply 3x times 2 and double it, do I get 12? 3x times 2 is 6x, 6x times 2 is 12x. Oh, this is a perfect square trinomial. So I'll put the 3x in the front, the 2 in the back, and since that has subtraction, that'll go right there. 3x minus 2, the quantity squared. Then I go to number 8, and the first thing I realize is that negative has to come out of there. So I'm going to pull a negative out, and that'll reverse all the signs that I see in my trinomial. And then I want to see whether or not that's going to be factorable. Well, there wasn't anything else I could take out as a greatest common monomial factor besides the negative, and it's not a perfect square trinomial, but maybe, just maybe, I can find two numbers that multiply to positive 72 and add to negative 17. And the first two that pop into my head are negative 9 and negative 8, because that's way back from your multiplication tables that we think, oh, 72, 9 and 8. Let's go to number 9. Number 9 looks like there's some stuff we could take out of this one, and we definitely want to. So we can take the negative out, and all of those are multiples of 5. So we'll take that out. And they all have an x, so we'll take that out. And that would leave us with y squared plus 6y plus 5. And then we'd go ahead and try to factor that. So we've got a negative 5x in front. And in the back, I notice those are not perfect squares, but I do notice there are two numbers that multiply to 5 and add to 6, and that's 5 and 1. So y plus 5 and y plus 1. Number 10, you take a look at it, and you should be thinking, wait a second, doesn't 16 go into 64? Because it does, 4 times. So we'll pull the 16 out. And we have to do that, by the way. If we are able to factor out a greatest common monomial factor, we have to. So it's 16 times the quantity x squared minus 4. And I notice, hey, those are perfect squares, but there's no middle term. So that's our difference of two squares pattern that gets factored as x plus 2 and x minus 2, so that outside times outside and inside times inside would cancel out. Now we're at number 11. This is the one that's going to take a little longer because there is no greatest common monomial factor. And 4x squared, that might be a perfect square, but negative 15 isn't. So I have to try all the combos here for 4. There's 3 of those. And then in the back, I need all the combos for 15, but it has to be a negative 15. So that means one of them has to be negative. So that makes this a little bit more to check through. And I start thinking, okay, I need a negative 7 in the middle. How could I get a negative 7 with the numbers that I have here? And I realize a 12 and a 5 would be really great. So I start looking, and I find it right there. Outside times outside is 5. Inside times inside is negative 12. And when you add those together, you will get a negative 7. So to factor this, this is front times front, so x and 4x. Last times last, negative 3 plus 5. And now all of these could be checked by doing FOIL. So you need to do FOIL on them. You need to get back to the original problem that you had. And that's a good way to check any of these factoring problems. Now the directions change, and it says solve each quadratic equation by factoring. So don't forget that you're solving here. You're not done when you factor. You have to figure out your zeros. So I look at number 12 and I realize it's got a 0. Can I pull a greatest common monomial factor out? No, but this is a perfect square. And this is a perfect square, 3x squared and 2 squared. And there's no middle term, so it must have been 3x plus 2 and 3x minus 2 equals 0. And I need to know where those zeros are. So I will subtract 2 from each side and divide by 3, and I get negative 2/3. And then on the other one, I will add 2 to both sides and divide by 3. And I get a positive 2/3. So that's how you solve. You have to keep going until you have where the x values would be when this graph is going to cross the x-axis. Number 13, 5x squared minus 22x plus 21 equals 0. Well, at least it's a 0. There is not a greatest common monomial factor. These are not perfect squares. So this is one where I better leave my space here. We're going to need to write down the combos in the front that give us 5. That's not too bad. But in the back, they have to multiply to positive 21, but somehow add to a negative 22. So that means they are both negative. Well, the good news is there's not a whole lot of them to check there. So for negative 22, let's see, 15 and 7 would do it. Outside times outside is negative 7. Inside times inside is negative 15. And then it's first, first, last and last, and find your zeros. So for this one, x equals 3. For this one, you probably want to write it out, add the 7, and divide, and get x equals 7/5. Number 14, x squared minus 12x plus 32 equals 0. So there's no greatest common monomial factor. 32 is not a perfect square, but I'm hopeful that with a little bit of effort here, I can figure out what my factors will be by good old-fashioned factoring. So I need two numbers that multiply to 32 and add to negative 12. That would be negative 8 and negative 4. So my zeros are x equals 8 and x equals 4, like that one. Number 15. This one, I'm looking for a greatest common monomial factor because it's already equal to 0 and I don't see one, but then I think, wait a second, 9x squared is a perfect square and 1 is a perfect square. If I take 3x times 1 and double it, do I get 6x? And the answer is yes, absolutely. So this is a perfect square trinomial with a 3x in the front and a 1 in the back, and because this is subtraction, it's going to be 3x minus 1 squared equals 0. So I need to know when 3x minus 1 equals 0, that would mean I have to add 1 and divide by 3, and that will be when x equals 1/3. That is the practice test for Algebra 2 for the test of basically 4.1 to 4.5. If you need to, watch it a couple of times, pause it, try to do the problems yourself, but be ready for the graphing of the quadratics, anything that deals with the quadratics, which would be problems 1 through 5 on the practice test for Thursday. And then for Friday, 4.1 to 4.5 test, well, that's really the rest of this, which is going to be the factoring and the solving using factoring.